Good morning, students. Today we shall discuss the topic of biasing. Yes, this is a very first step of designing a transistor-based circuit. Now, at the very beginning, what we are trying to find out, what is biasing really? What this word means. Listen, I am going to explain you briefly in a very short time what the word biasing means, right? You know, I have already shown a picture here. I hope you can see the picture in your laptop. This is a picture of a signal. Now, why do we have transistors? Normally, the basic reason, or rather, I should say the first reason that comes in our mind is to amplify a signal. Example, the signal coming from a mic. The mic sound is small, so that electrical signal has to be amplified. And today, for the timing, you assume that this is a signal from a mic. What you want is that output also should be like this, not even like that, it should be larger. Output should be, if input is small, like if input is small, then output should be large. That is the idea for which that is what comes to our mind when we think of a amplifier, right? Now, we also know people have said us that if you use a transistor, you can make amplifiers. So I'll take this lesson right on your laboratory method, experimental method. So we need a transistor. Firstly, when you need a transistor, you will go to your laboratory and ask that how do you choose a transistor? There are thousands of transistors lying around in the market, and there may be a few hundreds in your laboratory. Of course, each transistor is different from one to other. How do you select your transistor? For that, really, you have to take assistance from your laboratory teacher. If you go to your laboratory, you will find the transistor manuals. And the oldest and most renowned transistor manual is called Tower's Manual. Actually, it was published by many years back. It was published by a publisher called Tower Publication. Anyway, it was published from Europe or America, somewhere. Anyway, there you will find, in that manual, you will find all transistors and their detailed specifications. Nowadays, you can go to Google search also and find out transistor specification. But for going to Google search, you have to know the transistor type number. But in Tower's manual, the type numbers are given alphabetically as a dictionary, and in the various columns, all various characters of the transistors are given, and you can select your one. Anyway, that's a long story. Today, let us take a very common transistor. It definitely you have it in your laboratory. Let us take BC547. BC547 is a very common NPN transistor. So I take this BC547 right in front of you. I think you can see how I am doing it, how exactly I am doing it. This BC547 transistor I have chosen, I have placed it here, right? And as I suggested you earlier, all of you should have this software, and it's an educational version, students version, available free of cost. Now, when you have this transistor, this is the NPN transistor. You can see from its schematic diagram. And NPN transistors, this collector here should be connected to some positive potential, right? So let us get a positive potential here, right? So let us take a positive potential here. Let us make it, let us make it 10 volt. 10 volt is a nominal value for transistor operation. Let's take it 10 volt. And 10 volt is a nominal value for transistor operation, normal audio transistor operation. You should not use more than 15 or 20 volt in your laboratory, because up to 15 volt it is safe to use in your laboratory. You will not get any DC shock. And 10 volt is a nominal value. And what do we do? We connect the emitter to the ground, right? We connect the emitter to ground. If we do this connection, now we do not connect the collector to the power supply directly, because there is no current limiting resistor or impedance here. And a huge current may flow through this transistor and burn off this transistor. And in software simulation, it will give you an alarm that there is a problem. But practically, transistor will become hot and it will burn out. So we put a resistor here. Put a resistor here, and I put a of register of 1K here. Register of 1K here. Put a register of 1K here, and you may ask me that how do you decided 1K? This decision you will learn when you learn the your design criteria, right? Today, I am just giving you 1K. Trust on me. Now 1K will work. Now we give a signal source to the input of the base. Base transistor base is the input. We give a signal source here. So what do we do? We get a DC source, DC power source. Sorry, not DC power source. We have to get a signal source, AC power source. We have to get a AC power source here, right? And I remove some of this, what is written here, because all this writing will be make it cumbersome. It remains is only the voltage value and the hertz. Frequency, I take 100 hertz. Sorry, frequency I take 1 kilohertz. So frequency become 1 kilohertz, because these amplifiers, they are supposed to amplify power signals. And signal, normally our audio signal ranges from around say 100 hertz to maximum to 10 kilohertz. But normally when we work in our laboratory, we test everything on 1 kilohertz. 1 kilohertz is a nominal value, right? And the voltage value is 120 volt RMS. Of course, this will be dangerous to this transistor. And because this voltage, I'll not run the simulation, I'll just connect and show you. If you connect this, then 120 volt will appear across the base emitter junction. So obviously base emitter junction will burn, because base emitter junction has got only base emitter resistance, which is around 20 to 25 ohm. So And also other way, your signals are not in terms of volts. Signals are always in terms of millivolts, right? So let us take 1 volt. Let's take 1 volt RMS. 1 volt RMS will make 1.5 volt peak, right? So this signal goes into this. Now let us see what comes at the transistor output at this collector. So for that, we connect an oscilloscope here. An oscilloscope here. The oscilloscope, one input I connect to the source and another I connect to the transistor output. And I make this transistor output color blue color so that I have got two different traces in the oscilloscope and you can understand. Now let us see whether this signal will be amplified and output is available in the blue terminal or terminal B of the oscilloscope. Let us see how it works, right? So I switch on the display of the oscilloscope here and I run the system. See, it is showing there is some simulation error, right? So what I do, is 1.5 volt, 1 kilohertz. I'll increase it a little bit. It's still showing a simulation error. But whatever is the oscilloscope shows, I'll expand this. Of what it shows really, right? Let me see whether I can zoom this oscilloscope. In fact, you can see this oscilloscope. Red one is the signal, and the blue one is the output, whereas output is not at all as per the signal input, right? 1.5 volt RMS, 1K, and if I increase a little bit more, 2 volt RMS, 1 kilohertz, let's say, right? Whatever it is, I'll expand this display for you. See, this red one is the signal. Red line is the signal, right? And output, if you want to see further detail how the output looks like output, this is the blue line. I'll reverse this oscilloscope screen. The blue line is the output, right? Now, why this has happened? I did not get the signal output. And also simulation was showing that wrong. Software was showing there is something wrong. Why it happened like this? Now, I do one thing. I'll increase this red line, then I can explain you what really happened. Let's see. This red line is in positive half, right? When the red line is in positive half, then this base was forward biased and there was a base emitter current flow. That means when the base is forward biased, there was a base emitter current flow. And this flow of current, base emitter current, was amplified to collector current. There was a collector current here, right? And you know, collector current is beta times the base emitter current, collector current. And when collector current flows, then obviously potential of this point, that means transistor collector, drops below 10 volt, right? And otherwise, when this sinusoidal waveform This red line is negative. When the red line is negative, then the base emitter junction is reverse biased. Base emitter junction is reverse biased and no current flow flow through the base emitter, and obviously the current through the collector is also zero, right? Means this system will not work. If you just get a transistor and connect a signal to the transistor base and try to take the output from the transistor collector, this will not work. Simply, it will not work. So you need to have some other technique. What is that technique? Let me check this. Now I'll remove these diagrams. They are no more needed. Some other technique is needed. So let us see what is this technique. Now, this 10 volt and collector resistor is sacrosanct, is always needed, right? Now, what I'll do, I'll bring this, make a little space here so that I can design the circuit on the left hand side. So what we found now, that this base, when we only the positive half cycle conducts, negative half cycle does not conduct. And let us say the negative half cycle, if it is 2 volt RMS, then negative half cycle is 2 multiplied by root 2 is something like 3 volt peak, is something like 3 volt peak. So what we should do, what we can do, if we give a DC potential here at the base of value approximately 3 volt or more than 3 volt, then what will happen? When the signal is positive 3 volt, the voltage here will be 3 plus 3 is 6 volt. That means, okay, let me give a DC power supply, then you will understand what I'm trying to say. This is a power supply, and this is a power supply. I'll not run the step circuit because it will be wrong. If I provide a DC power supply here, 12 volt, I do not need 12 volt. Let us say I take only say 1 volt, and this value I reduce to 0.5 volt RMS, 0.5 volt RMS. And if I connect it like this, then what happens? This base is already at plus 1 volt, right? And this signal source has 0.5 volt RMS. That means 0.5 by root 2. It is something like 0.75 volt peak. So positive half cycle will be 0.75 volt, which will be added to 1 volt. So it will be 1 plus 0.75, that is 1.75 volt, and the current will flow through this base emitter junction. And the negative half cycle, when it will be minus 0.75, then this is 1 volt here. 1 volt minus 0.75, still it is minus 0.2 volt. So this base emitter junction will still conduct. Now, you might have already caught me that what I have said is something impractical. Because this base emitter junction, if it is a silicon transistor, this junction barrier is around zero point 0.2, from zero point 0.2 to 0.25 volt. If it is a germanium transistor, the barrier is zero point 0.6 to 0.75 volt. So the bias should be enough to circumvent or to cross over that barrier also. So I adjust these voltages. This voltage I make 1.2 volt, and don't ask me now how to decide 1.2, because I have some experience of transistor amplifier designing. When you also will learn designing, you will automatically guess what should be the value. And this value I make 0.2 volt RMS 1 kilowatts. Then what happens? This is 0.2 volt RMS, and so its peak value is 0.2 multiplied by root 2, so it will be the 0.3 volt RMS. So this is 1.2, and this is plus minus. I'll put it here. This is, I think this will be clear. This is plus 0.3 or minus 0.3. This value is plus minus 0.3. So when it is plus 0.3, potential area is 1.2 plus 0.3 is 1.5. So this base emitter junction will conduct. When it is minus 1.3, then it is 1.2 minus 1.3. Then what remains is 0.9 volt, which will also conduct to the base emitter junction, even if it is a germanium transistor. Right? So this will conduct. We shall see whether it really happens so. Now, I'll remove this text from here. Then I go to then I cannot test this circuit right now, although it appears everything is done, because there is something more which is essentially missing. Already possibly guessed that a AC voltage and a DC voltage does not get added up like here, like this here. You can try it in your laboratory. Take a small AC voltage and take a small DC voltage, less than 1 volt, so that there is no accident. You will see it does not work. It does not. This is number one. So what we have to do, we have to put a capacitor here. We have to put a capacitor here. We go to the capacitor and take a small capacitor, 1 microfarad capacitor, and connect it here. What will happen? This DC current will not be able to flow into the AC source. That would have been dangerous. The current will not be able to will flow through the AC source because of this capacitor. DC current will flow only through this. This is number one addition. Addition. AC current from here, when it comes through the capacitor, then it has two paths. One path is this base emitter junction. Another path is through the DC battery. Now, possibly you have already learned that a DC battery is always a short circuit for our AC source. This is a very, very important information you must always keep in mind. A DC source is always a short circuit for a AC source. So what will happen? This AC current from here will go through this short circuit path, and nothing will go through the base emitter junction. So it will not work. What you have to do, you have to always put a guard resistor here in the battery path, right? So Once again, you can take a small resistor, but you have to take a resistor. I take a 100 ohm resistor. I take a 100 ohm resistor, and this 100 ohm resistor I connect here. Then what will happen? AC current will have then two paths. One is 100 ohm path, another is base emitter junction. Now, base emitter junction resistance is of course much smaller than 100 ohm. So enough current will flow through this base emitter junction. Now, you may ask, can I make this 100 ohm larger? If you make it larger, then that will be a problem for this DC voltage, because this DC source will not be able to supply enough current through this. So I have made two additions. One is this capacitor to isolate the signal from the DC source. Next, I have added this resistor so that AC current does not get a short circuit path. Signal current does not get a short circuit path. One thing more I shall add. I shall add a resistor here at the emitter. Why? See, base emitter junction resistance is very small. So, if your measurements of signal and this DC voltage is not good enough, then this will be a short circuit and the transistor will burn off. So, always you connect a small resistor at the base emitter, at the emitter to ground. So, you make this arrangement. So, three things I have added and above biasing. Biasing was just to add this DC voltage. But since I have added a DC voltage, I have added three more things. One, I have added a emitter resistance so that the base emitter junction is safe. I have added a capacitor so that the AC and DC supply are isolated. I have added a protective resistance 100 ohms so that huge current does not flow through this. Now, what I shall do? Now I will bring this capacitor, bring this oscilloscope. Input of this oscilloscope I will connect to the signal, and channel 1 I will connect to the signal, and channel 2 I will connect to the output, transistor output from here. And I'll make this transistor output color blue so that I can easily identify which one is the input waveform, which one is the output waveform, right? So I will put it there. Earlier, it was like this. It was a sheer nuisance waveform without biasing. Now, with biasing, what happens? Let's see. Now, with biasing, I have these two waveforms. I do not know whether you can see the oscilloscope settings because these are so small writing. Here, I'll increase the y-axis amplification. This is channel input I have increased. The output also I increase. But if I increase the output, you see, output here, this is a 5 volt per division. So it is already at, average is at 5 volt. It is already average is at 5 volt, right? Over 5 volt, there is an oscillation. Why? I will explain you. Let us see, let us put a current probe here. Let us put a current probe here. And unfortunately, this probe cannot be, the script of this probe cannot be amplified, cannot be zoomed in. Let me see whether I can zoom in. Some zooming in possible. This probe will measure the current here, current through the collector, right? If I run it, current through the collector is 4.9 milliampere, right? I don't know whether you can see this, but if you do this simulation in your own laptop, you will be able to see everything. 4.9 milliampere, let's say 5 milliampere. So if current 5 milliampere flow through this, now I zoom out. If 5 milliampere current flow through this collector, 5 milliampere current is flowing through this line, then what is the drop here? 5 milliampere into 1K is 5 volt. And what is the potential here? 10 volt. So, even without signal, potential here is 5 volt. That is why you see it is 5 volt here. This is the average 5 volt. And when the signal comes in the positive half, let's see, in the positive half, the transistor conducts and current becomes more than, it was 5 milliampere, current becomes more than 5 milliampere. If current becomes more than 5 milliampere, then this potential drops further. Potential of this collector drops further. So in the positive half, the output drops further than 5 volt. And the negative half, when the negative signal current flows in the opposite direction, then potential of this transistor collector goes up. It goes up. So that is why it is average 5 volt and then goes up and down. Right? So what we can do at the output, I connect a DC separator. I connect a capacitor, right? Sorry, not this line. This was the input line. The oscilloscope, I put the oscilloscope wire a little up so that you don't have any problem to see. And this is the capacitor. I do one thing. I put this oscilloscope line up so that you don't have any capacitor. I connect here and then I connect it to the oscilloscope. Color blue, and I put another resistance here and I put another resistance here so that the output AC voltage falls across this resistor. This resistor, of course, has to be very high, comparatively much higher, 10K. So this AC current will flow through this 10K resistor, and I should get here only the AC voltage. That is the idea, right? Now I run it once again. I reverse it so that you can see properly. Now you see, I am getting the blue line, only the AC voltage, right? Now, if you see this if you can read this oscilloscope reading, the channel A is set at 200 millivolt per division. I make it slightly more, channel A, 100 millivolt per division, and there are how many divisions? Approximately 1, 2, 3, and 3, 6 divisions. So it is about not 6, about 1, 2, 2.5, and 2.5, 5 divisions. So 5 into 100 is 500 millivolt peak to peak. And the blue line is set at 5 volt. I make it 1 volt. So blue line is 1 plus almost two and a half into 1 volt, that is 2.5 volt peak to peak. Blue line is 2.5 volt peak to peak, whereas red line, that is the input, is only 600 millivolt peak to peak. So there is a huge application, huge gain. One thing more, here, one thing more you have noticed, there is a phase difference between the input and out. That phase difference is due to this. This is due to this capacitor, right? If you learn later how to select this capacitor, I'll show you. If I change this capacitor to say 1 milli, then the due to this capacitor, the output also will change and the phase also will change. Why the output will change? Because capacitor is a kind of a impedance in the signal line. So let us see how they have both changed. So see, now the phase difference is almost zero, right? And here, now I will explain you once again. When the red line, that is the signal, is positive, then the output is negative. That is because due to the DC bias, a fixed voltage of 5 voltage appear here, and when there is a signal current flows in the forward direction in the positive half, then the current flows from the power supply to the ground, and this potential increases. So obviously potential of this junction decreases. So when signal increases, output decreases. And in the negative half of the signal, just the reverse occurs. Now, you will see one thing. This is so what you get at the output. We got at the output exactly the amplification that you wanted, number one. Output signal also we got a sinusoidal AC signal, and there is a 180-degree phase reversal. This 180-degree phase reversal is the basic property of a transistor. The reason I have already explained, because when the signal increases, potential here decreases. And when the signal is negative, potential here increases. Now, this method, first question we started is, what is bias? With biasing. We started biasing. Now, I repeat once again, what I have shown you here is not as per design criteria. I have only shown you what is biasing. Right? When you learn design criteria of a transistor amplifier, you will see exact this waveforms will be further fine-tuned. So what is bias? If you want to write what is biasing, biasing is a technique to provide a DC voltage, provide a DC voltage at the base of the transistor, transistor at the base DC voltage of appropriate polarity of why I added the word appropriate polarity? Because had this been a PNP transistor, Then, of course, the base was a N-type semiconductor and emitter would be P-type semiconductor. So forward biasing, then this potential has to be negative. But anyway, this technique of providing DC voltage of appropriate polarity and appropriate value, appropriate polarity and value. Biasing is a technique to provide a DC voltage of appropriate polarity and value at the base of the transistor. In base emitter, in common emitter, this here emitter is the common, and input to the base, output from the collector. This is for called common emitter configuration, which possibly you know already. So, and now in our next lesson, we shall learn what are the actual techniques of biasing. Because here I have used a 10-volt power supply. Here I have used a 1.2-volt power supply. And as an engineer, if you are an engineer, nobody will allow you to use two power supplies for a single amplifier. Right? It is just not possible. It will be too costly. So we have to use a single power supply, 10 volt, 12 volt, whatever it is. And out of this single power supply, we have to design the appropriate bias. In our next lesson, we shall learn what is the value of appropriate biasing. What is the appropriate value? Appropriate polarity is very clear. What is the appropriate value and how to do it, right? And there could be many techniques, but two or three very basic techniques are most prevalent and used everywhere. You should learn it in the next lesson. Fine?